Hello, Aman. Am I audible? Aman, can you please respond? Am I audible? We'll wait for some time. Let's see if others are joining the session. Okay, let's get started. I'll just share my screen. Okay, my screen is visible, right? So I'll just revise the weekly lectures and then I will have some tutorial exercise. So if, in case if you have Aspen which where you can simulate at this moment, so just keep it open. Okay, we have a few examples which we can try today. Okay, so yeah, okay. So Professor was discussing about TXY plots in the last week lectures. He discussed about binary mixtures and okay. And then, yes, there was discussion about the sensitivity analysis, design spec toolbox, and optimization, and the simulation of the data fitting regression. Essentially, those things were discussed. And then, yeah, so essentially, he is now slowly shifted from the simulation to the property analysis, and then regression, optimization, so on. So, in today's session, we'll try simulating a simple flow sheet, and then the use of optimization and the sensitivity analysis. Also, we'll try to cover these two aspects too. Okay, fine. So, before just going to the simulation thing, I have very few questions. Okay, so these questions gives me a clarity about you are able to follow the lectures or no. So please do answer these questions. Meanwhile, you can keep your Aspen ready. We'll just get started with the worksheet. Okay. So this is one of the question. So change of pressure suitably helps in the separation of the azeotrope of water and the acetonitrile. Is it true or false? What about others? Okay, so what kind of azeotropes are separated using the pressure approach? What are the kinds? Okay, the first question is what are the kinds of azeotropes do we have, and what kind of azeotrope is separated using the pressure swing approach, whatever we have just seen? Any response? Sorry, I couldn't get you. Acha, okay, so you mean binary azeotrope can be any binary azeotrope can be separated using the pressure swing approach, is it? That's what you mean? Or not swing, pressure using two different pressures. Is that what you mean? Okay, so okay. Is there any other classification with respect to exhibition of VLE and VLLE? Okay, so have you heard of homogeneous and heterogeneous azeotrope? Anyone in the class? Have you heard of? Yeah, correct. So homogeneous azeotrope means it's the VA. Sorry, Yashwant, yeah, you are telling something. Correct. Yeah. So yeah, I know in one of the session I was explaining about the Gibbs free energy and the minimization of Gibbs free energy, how the Gibbs free energy minimization results in this formation of homogeneous and heterogeneous isotope. So yes, no, it's one way of explaining this. Correct. So how do I separate a homogeneous azeotrope? Let's say if I have two components A and B, both form a homogeneous azeotrope. How do I separate them? Okay, so homogeneous azeotrope means the azeotrope is VLE. Okay, you have only vapor liquid equilibrium. If you what do you mean by heterogeneous azeotrope means you have VLLE. Okay, essentially you have a split of liquid liquid L1 L2. So if I have a homogeneous azeotrope where I have a VLE mixture. Okay, let me show you an example in internet itself. Water and ethanol. See, if you see the TXY diagram of water and ethanol, it will be like this, okay? So it's the homogeneous azeotrope. This is another example of a homogeneous azeotrope, okay? So in this case, how do we separate the two phases? How does it help? Can you explain the process? How by changing the pressure can we separate? Correct. You're on path. Can you complete this statement? You're almost there, Yashwant. Just try finishing it. Okay. 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 So, and what about heterogeneous azeotrope? Anyone, any other candidate can respond? Others? See, he gave answer for one, right? I'll explain it in detail and just meanwhile, can you answer how do we separate heterogeneous azeotrope? Others, other than Yashwant, preferably, because you have already answered one question. Okay. Okay. So, if you have two liquid phases, which are, they're immiscible kind of thing, right? So, why to add an additional component? We can just separate it at the height at which we have two layers, right? What do you say about it? Why do we need to have an additional component? We already have two liquids. Yes, two liquid phases are already immiscible. So, why do we need that? Yeah, we already have interface between two liquids, so we can just directly separate it, right? However, both the liquid phases will have the components which we are interested in. So what do we do in that case? Think over it. This will help you in the sequencing problem in process design. Freezing, you mean crystallization? Crystallization is used, I'm assuming the freezing word is used for crystallization in this thing. Crystallization is normally used when you have boiling points of two components very close to each other, where distillation becomes very costly. For example, ortho and paraxylene. So separation of these two components is normally carried out by crystallization, where your boiling point difference is about 2 to 3 Kelvin, if I remember correct. I don't remember the exact values. So the difference will be too less. So distillation becomes quite expensive in this case. So then in that case, crystallization is normally used. However, these two components don't form azeotrope. Okay, you can get it as pure thing, pure components. They don't form azeotrope. Okay, anyway, let me just show you. So the answer is this is with respect to homogeneous azeotrope. So if you increase the pressure, so this plot is the TXY diagram drawn at different pressures. Okay. Uh, while you go up, the pressure increases. Okay. As you can see, the bottom one is 1 bar, and next one is 5 bar, and then this is 10 bar. This is 20 bar. Okay. There are other figures above which above these four curves. However, I have plotted only few here. So you can see this 1, 5, 20, and 10 and 20 for with respect to y. Okay. And this is with respect to x. So as the pressure increases, as Yashwant mentioned, the temperature increases. Okay. At the same time, the location at which you have azeotrope also changes. Right. See, it's changing. It's getting shifted. So now if I have a column at this operating pressure, this is 5 bar, right? If I have one column over here, which is operating at 5 bar, one of my product will be component A, and another component will be the azeotrope from the distillation column. So if I have an intermediate feed to the distillation, one of the product will be this one and another will be azeotrope. So now I'll change the pressure. I'll decrease the pressure to 1 bar, which means I'm on this curve, right? And separate this mixture in a different column which is operating at a different pressure. In this case, this is 1 bar. So now I have a product B as one of the output and and homogeneous azeotrope as the another product. Again, I'll increase the pressure. So now I'm in this zone, right? So now I'll get another product. So essentially, between two columns, I have this azeotrope circulating and giving me two pure components from two columns, right? So this is how azeotrope is separated using pressure. Could you get it? Could you follow whatever I have explained? Okay, fine. Yeah, see, yes, the location of azeotrope is getting shifted. You see, at one bar, we are not breaking azeotrope. We are just shifting the azeotrope. That's all. We are just shifting the location. Location means with respect to the composition of these two components, we are shifting. For example, let's say on LHS, if we have A and RHS, if we have B, initially at one bar, we have azeotrope at about 33%, right? And then when we increase it to 5 bar, the azeotrope is about 42 to 43%, right? So we are shifting the composition of the components, and this is about 50%. So azeotropic composition is changing with respect to pressure. So using this, we design the distillation columns for getting both the components. Could you follow now? Correct. Yes. Uh, one side of the column will have azeotrope. One side means either the top product or the bottom product. We should make sure that both sides we don't have azeotrope. That's all. So one side we should get pure component, and the other side we should get the azeotrope. That's how the column pressure should be designed. Yes, yes. We can't get stuck. In normal distillation where we don't have azeotrope, two components can be separated using one column. However, if we have azeotrope, we won't be able to separate them. We need two columns for two components because we have azeotrope at the other end. Okay. Yes, if you have azeotrope, if you want to do the separation using pressure approach, you need two columns. Correct. Hmm? Sorry, I couldn't get you. No, who is speaking? I couldn't get. Yeah, Yashwant. Yeah, yeah. Please. Okay, see, uh, let's say if we are operating at 10 bar, right? This is the TXY plot which we'll be following. So if we have a feed at this location to the distillation column, one of the product will be your A component, which is on the left hand side. However, the other product will be azeotrope, right? So one side of the column you will get pure component. However, other side of the column you will get azeotrope. It's not the pure component. Azeotrope is a mixture of both A and B. So now you need another column for getting the component B. Did you get it? No. Huh? Okay, great. Thank you. Possible. Yes. Accordingly, it will change. Depending on the azeotrope temperature and the composition, you need to design the sequencing. And RCMs will be useful in designing this sequencing, residual curve maps, because you will be able to see at what composition and the temperatures you are getting the azeotrope, and dividing the RCM with bifurcation things will help you out in which region of the RCM you have to put columns and all. So that is a different course itself about sequencing the distillation columns. Yeah. Yeah. Who is this? Yashwant. Okay. Yeah. Tell me, Yashwant. Correct. Correct. Yes. See, in your mass transfer course, you must have seen when the two curves intersect when your XY relation intersects the equilibrium line, that's where your separation ends, right? So similar to that, wherever the bubble point curve and the dew point curve are intersecting over here, that's where your separation ends. Okay. So for the second part of the curve, you need another column for separation. Yeah. Okay, fine. Yes. So can you answer this question? The activity coefficient for an ideal system is? Yeah, yeah, correct. And what about the Pegacity coefficient? Others do respond, yeah. Only two of you are responding. What about others? You're following lectures, or the question seems quite easy for you? Okay, Sachin, thanks. You have given all your Sanjay. No, if the given system is forming azeotrope, then how can you break azeotrope with only two components in the pressure approach? If you have one additional component which breaks the azeotrope, that is a different case. However, in this example where we are separating two components only using the pressure, then it's not possible. Not Pegacity, Pegacity coefficient. Can you justify your answer? Because one says it's greater than one says less than one. Oh, it's only you. Sachin, can you justify your answer? Yeah, Yashwant. What issue you have? Then others should answer. How can I answer about this? Others, is my voice continuous or you have similar issue? It's clear, right? Okay, I think Yashwant, it's only issue with you. Just do one thing. Just disconnect and rejoin the meeting. That may help. Okay, fine. So with respect to this, yes, it is equal to 1. I expect an answer from you about the figacity coefficient. Okay, do let me know. Fine. So, in the case of this is an example. Okay, nitro is nitroethane, right? Nitroethane, cycloheptane, and ethanol mixture. So, what does it form at the standard temperature and pressure? How do you know this? The given components, whether they exhibit VLE or VLLE, how do we decide? So in this case, I have three components: nitroethane, cycloheptane, and ethanol. How do we know what is the thing which the given component are exhibiting, whether it's VLE or VLLE? How do we identify that? No, we are talking of identification of their exhibition, not about the distillation sequencing. That comes much later, distillation sequencing. So you must have seen how do we identify azeotrope in Aspen, right? Did you? Did you see that? Yes, right. So which means for the given components, you know whether they form azeotrope. If they form azeotrope, what kind of azeotrope is it? Homogeneous or heterogeneous, right? So accordingly, you can decide, okay, which model, which one to use. So in this case, as you see, from azeotrope, while checking azeotropes, we can see that it forms VLLE thing. Okay, so from there you'll be able to identify. Um, so this is just a simple question. The ternary mixture of nitrogen, oxygen, and argon can be separated through cryogenic distillation. Is it true or false? Just answer this question. I'll just come in a minute. Okay, so some say it's true. What is cryogenic distillation? Whoever have answered. Distillation below 0 degrees, distillation at very low temperature. Okay. 0 degrees centigrade, Rankine scale, or which scale you are? Okay, 0 degrees centigrade. Okay, at very low temperature, can you quantify the value, Sachin? What about others? Sanjay, Aman, what do you think? Oh, Sanjay has answered. Okay, sorry. Sachin has also answered. Aman, what about you? Yashwant says it's below 0 degrees. Okay. Aman, are you in class? High pressure, low temperature. Okay. Now, Sachin, you are giving quite qualitative answers. Can you just quantify if possible? Give me a range that is sufficient. If you're telling high pressure, is it about 10 bar or 20 bar or 100 bar, 1000 bar? What pressures you're talking of? And similarly, the low temperature, is it 300 Kelvin, 200 Kelvin, or 100 Kelvin, or 1 Kelvin? Just quantify it. Okay, so what is cryogenic range means any temperature below 123 Kelvin. Okay, any temperature below 123 Kelvin is called cryogenic range. Okay, so in this particular question where you are asked to separate nitrogen, oxygen, and argon, uh, all the components have the boiling points below 123 Kelvin. Okay, so if I remember correctly, nitrogen has about 77 Kelvin, oxygen argon will be about 83 and 86 Kelvin respectively. Okay, so in that case, since all the temperatures are below 123 Kelvin, you need a distillation column operating below these temperatures. Okay, so thus the separation of these components comes under cryogenic distillation. Okay, and in few days, or in even we'll start from today's session itself, we'll do the air separation plant simulation. Okay, so this might be useful in to extend it where other cases also. Okay, fine. We'll just so yes, this is one of the cryogenic distillation operation where you have compressors and then the main heat exchanger where it is cooled to temperatures of about 100 Kelvin, then expanded in a turbine. And then you have distillation column. Normally, you see that distillation sequencing is done in the sequence. If you have three components A, B, C, the first column will separate A and the second column will separate B and C. However, in this case, the two columns are thermally coupled. Okay, thermally coupled means one of the condenser of one of the column acts as a reboiler of another column. The reason and all will just come back very soon. Okay, we're gonna simulate this exact plant information in our session. Okay, so during that session I'll explain what is the operating pressures required and why do we need to operate at those conditions, etc. Okay, fine. We'll come back to this process. Fine. So there's one of the question: water and trichloroethane form a miscible homogeneous binary mixture. Is it true or false? Can you open your Aspen and check this? In case if you have Aspen, just try answering this question. I'll wait for a few minutes, okay? You can just try solving this. It's not minus 123 Kelvin. It's 123 Kelvin. There is no negative temperature in Kelvin scale. The lowest value where you can go is 0 Kelvin. Okay, there is no negative temperature in Kelvin scale. It's 123 Kelvin. I'm not talking in degree centigrade. It's 123 Kelvin. Could you check it? What does it form? Fine, no, in case if you have open Aspen and checked the TXY diagram of this particular thing, you can see that you have liquid-liquid separation in this particular case, where below this you have liquid 1 and below this you have liquid 2. So it forms VLLE, okay? Fine. So this is kind of a trivial question. I'll skip it. Uh, so can you answer this? The curve 1, which is of blue color, what is it? What does this curve represent? Yeah, you are correct. It's bubble point. Yeah. What does the green color curve represent? Yeah, it's dew point curve. So in case if this is plotted against pressure Pxy, then what is the curve which is below represent? I mean, what does it represent? If it is Pxy instead of Txy, is it same or is it opposite? Uh, you are telling two different answers. Can you justify it? Whoever says it's the same, give me a minute, Sanjay. I'll explain it. Let me finish this. Uh, so Yashwant and Dharmaraj. So you have different answers, right? Can you justify your answer? Okay, you mean the curve which is below is the bubble point in both cases, and the curve which is above is the dew point curve in both Tx1 and Tx5. Is that what you mean? Okay. There was one, yeah, says opposite. See, Varma, can you justify your answer? You're stating it as an opposite. Okay. How do you know that? Yeah, the correct answer is yes. It will be the other way around. In case of TXY diagram, the lower one becomes the dew point and the above one becomes the bubble point. Whatever explanation you have given is inlined. Okay, so you are correct. It's the opposite. Okay, fine. So this curve, right? You wanted. So see, in case of homogeneous azeotrope, I have shown you an example here, right? See, it's quite smooth. However, in case of heterogeneous azeotrope, you have this kind of curve. It will be flat horizontal line. Okay. So from this point to this point, you have one liquid, and from this point to till this point, you have another liquid. So it's essentially L1, L2. In this region, you have V plus VL. In this region, you have V plus L. Okay. So you have four different regions in this. It's VL1, VL2, L1, L2. Okay. So this is how you read the TXY diagram for an heterogeneous mixture. Depending on the region, your phase will exist. Now, could you follow Sanjay? Yeah, you can present. I'll stop presenting. Please share your screen. You're sharing your screen, right, Sanjay? I'm waiting for you. This is XY diagram, not TXY. Can show the TXY plot. On the left of this, you have TXY plot. Okay, see in XY plot, whenever your curve crosses the equilibrium line, it's the proof of the system forming azeotrope. Okay. Uh, in case if it is quite horizontal, then you can say that it's VLLE. In case if it is kind of a curvature, you have a good curve, then it's homogeneous azeotrope. Okay. Whenever it crosses the equilibrium line, it's the proof that it forms azeotrope. Okay. Okay, fine. Let me continue. Okay, so we'll get started with this problem. Before this, how many of you have Aspen now? You are seven of you are here. Can you just answer? Sachin, you have Aspen. Sanjay, you have good. Sachin, do you have now? You don't have Aspen. Okay. One has Dharmaraj. Do you have? Okay. Two of you have. You don't have. Yashwan, do you? You have Aspen. Okay. So one. Yeah, please. Yeah, Yashwan, continue. What? Uh, no, I didn't get your question. Shwan. See, when you go to anyway, if I'm able, whatever I understood from your question, I couldn't get it completely. But when you go to the dew point curve at a given temperature, it will show you the vapor fraction. I mean, components composition in the vapor phase. At the same temperature, if you come towards the left on a horizontal line, you will have the composition of the component A in the liquid phase. Okay, so it's not the same. Huh? Is that what your question is? Correct. I mean, you're talking of dew point, so it will be in the vapor phase composition. It's not liquid phase composition. Yeah. Any other questions? No, right? Okay. So, whoever have the Aspen, we just try, we get started. Others, just take a screenshot of this. Anyway, I'll be sharing this PDF in a while. So, try solving this question, okay? And just we'll come back. So, in this process, this is the complete air separation plant which we are interested in. Since we won't be able to complete the entire process in a class, we'll divide it into three sessions. Okay. So the distillation part will separate it in a different class. The heat exchanger and the cooling session will simulate in one class. Okay, and the rest will simulate it in other classes. Okay. So essentially, we'll divide it into three. So if you observe the cooling and the liquefaction process, it will have the similar sort. Okay, there's one more turbine which is not shown over here. However, the actual process will be in the similar way. Okay. So now the basic idea is for us to find instead of taking air as uh, the component as of now, we'll just simplify it. We'll start with simple nitrogen. Okay. Later on, we'll increase the number of components. Just for sake of simplicity, consider only nitrogen. Okay. So now I want you to see. This is the flow sheet. You have a feed nitrogen. So nitrogen is entering at 5 bar. Let's start this one. Okay, let's start with the 5 bar example. So now I want you to construct a flow sheet where you have a turbine and a phase separator. To the turbine, you have nitrogen with a flow rate of 1 kg per second. Okay, it's 1 kg per second. Okay, nitrogen, which is at 5 bar. It is expanded through a turbine. Turbine has an isentropic efficiency of 70%. Okay,
Use two-phase expansion in turbine, which means you have both vapor and liquid. Use Peng-Robinson equation of state. Okay. Use Peng-Robinson equation of state, and then see what is the quantity of nitrogen which is liquefied. Okay. Just first simulate. We'll do the sensitivity analysis and design spec bit later. First, just simulate. Take nitrogen, which is at 1 pi bar and a temperature of 100 Kelvin. The stream 5 conditions are 5 bar, 100 Kelvin. It is expanded through a turbine which has an isentropic efficiency of 70%, which is a two-phase expander. Whatever output of turbine you have is sent through a phase separator where the liquid is separated from the bottom and the vapor is coming from the top. Now I want you to tell me the value of nitrogen which is coming from stream 7, which is essentially getting liquefied. Can you tell for this particular case? People whoever have Aspen with you? Yeah, yes, please, Miraj. Yeah, please continue. It depends on what you're using. For example, see, isothermal is the one which is most preferred, okay, because you have a minimum work of compression in that. In case if you are talking of compressors, however, it's very difficult to achieve isothermal. Okay, so instead of isothermal, you go with isentropic process with a particular efficiency. So with respect to compressor, in practical world, it will be about 30 to 50%. And yes, there are isothermal compressors which are used in. I'll give you one example, which is used for compressing air. Okay, so there they this is a different kind of compressor, not the screw or scroll kind of compressors or rotary. This kind of compressor where you have water inside the chamber and the volume of chamber is decreased. At the same time, you have water shower from the top. Okay, so you have no, 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 no. It's the air compressor. You have on over the air, you have water shower continuously showering. Okay, so you have water shower on the top. You have air. You have water bath below. So now the volume of this particular tank is decreased. Whatever the temperature of air is getting increased is cooled down by the water shower. Okay, so this way you are trying to maintain the compression process at a constant temperature, essentially an isothermal process. So yes, there are compressors. where you can achieve a compression process isothermally. However, it's not that economical. Okay. Yeah. It's mostly polytropic efficiency or isentropic efficiency, roughly about 50%, 30 to 50%. Correct, correct. Isothermal is the ideal case. That's what I'm telling. When you're talking of ideal systems, they are very difficult to achieve. Even if you are trying to achieve the cost of the product which you need to put in is very huge. So with respect to industries, those are not preferred. Although your operating cost comes down, your capital cost is very huge. So those kind of compressors are not preferred in industries. For small scale applications, yes, you can do that. So others, just try solving this question. So I'll just repeat it. The feed, which is the steam 5, has a flow rate of 1 kg per second of nitrogen at 100 Kelvin and 5 bar. It is expanded through a turbine which has an efficiency of 70%. Okay. Use a two-phase expander. Use Peng-Robinson equation of state. Here we are only dealing with respect to nitrogen just for the sake of simplicity, only for today's class. The outlet of the turbine is sent through a phase separator where the liquid phase and the vapor phase are separated. Now, with respect to this, I want you to identify what is the quantity of nitrogen that is liquefied, which means the fraction of the nitrogen which you are able to get from stream 7 to the stream 5 of the stream 5. Okay, it's the ratio. Now, I'm asking you the ratio of mass flow rate of nitrogen from stream 7 to the stream 5. Okay. Asha, six of you are here. Of the six, how many of you are solving this question now? Sachin, you are solving. Okay. Yashwant, Sanjay is solving. Okay. Thank you, Sanjay. Dharmaraj, you don't have Aspen, right? Yeah, you told. Uh, Tripti Varma also doesn't. Yashwant is doing. Okay. Three of you are doing. Aman, what about you? Aman, are you on call? You're solving this? Do you have Aspen? You don't have Aspen. Okay, fine. So three of you have and three of you don't have. Okay. People, whoever don't have Aspen, is it possible for you to have by next week, or are you in of your office during this time and you don't have access to that? Is that the case? Next week, can you manage to get Aspen? We'll finish this question today, but next week, if you also have Aspen and if you can involve in this, it will be good, right? Okay, you are in office, so you won't be able to have access. What about Dharmaraj? Is it possible for you right now in office? Next week I may have. Okay, great. Uh, Aman, what about you? Next week, can you have it? No, no, not okay. I'm asking you. Is it possible for you to have? You don't have Aspen as of now. That's what I know that. For the next week, is it possible for you to have the access? Okay, fine. I know. Just finish up this question here, first of all. So, Sachin, you have value of about 150 kg per hour of chlorate of nitrogen as liquid. Okay, so the input is 3600 kg per hour, is it? What about you, Sanjay? What is your status? Sachin, can you do a sensitivity analysis by varying the input temperature? Initially, we have fixed it to 100 Kelvin, right? Do a sensitivity analysis, vary the temperature of the steam 5, and see at what temperature you are able to get the fraction to be 60% and 70%. Yashwant, you are telling it's 0.03. Okay, 1 kg per hour is the feed. Okay, so let me just divide this 149 point whatever. So it's about 0413. Both of you have different answers. How come? So have you taken the same isentropic efficiency, whatever I have mentioned? Some issue here. See, you guys have different answers. It can't be so. Correct. It can be kg per second, but the fraction should remain same, right? That's why I have divided it as 3600. Since he has used 1 kg, since Yashwant has used 1 kg per hour, so I have divided it by 3600. So it becomes the same. So both use 70%. Okay, let me try it out.
It's the zero bar pressure drop. If you are assuming one bar, that means you are giving the pressure or the outlet pressure, if I remember correctly. Let me just see the value. Output of the turbine is 1 bar. See, it says absolute value, outlet pressure value is greater than 0. Pressure drop if value is less than or equal to 0. So, yeah, you can write it can write it as 1 bar also. It means the same. So the value is 0.041. To, okay, so issue with the convergence. Okay. So, can you both run a sensitivity analysis and see at what temperature you have the liquid air yield of 60%, 70%? Can you do a sensitivity analysis in this case and find out the temperature, or just vary the temperature, okay, and see at what temperatures you are able to get the fraction as 60% or 70%. The fraction is M7 to M5, which is the flow rate of nitrogen in stream 7 to flow rate of nitrogen in stream 5. Sorry? No, no, Y is not efficiency. See, Y is defined above. Y means the flow rate of nitrogen in stream 7 to the stream 5. It's not efficiency.
You are able to do it? Okay, I'm waiting. Can you please carry? Still solving? Shall I wait for some more time? Okay, others? Yashwant and Sanjay, what about you? What about Sanjay? Okay, I'll just explain. See, here I'm asking you to vary this temperature of steam 5 and find out this flow rate, right? So what you're supposed to do is go to model analysis tool, sensitivity, click on this, new. Which one you want to vary? It's the temperature of, it's a stream variable, right? It's a steam 5 and its temperature. Change it to Kelvin. Let's say from 75 to 210 with an increment. Sorry, with an increment of 1 Kelvin. Okay. Now what do you define? You define M7, the stream Is the stream variable or the stream 7? This is mass flow rate, right? Check the units. This is kg per hour, so we'll give it as kg per hour. What do we table it? Fill variables, that's all. So after giving, just reinitialize this, save your file, and then run it. So just check the results. See, it says for different temperatures, you have different values. So this is what I have asked you to calculate. Let us change it to SI and run it again. See, for different temperatures, you have different flow rate of liquid nitrogen, right? So this is how you do the sensitivity analysis. Could you follow? Could you people follow? How did I do the sensitivity analysis? Okay. What about others? Yashwant, Sachin. Okay, great. Now the question asked you to is find the value at which this becomes 60%, right? So in this list, can you identify the 60% and 70%? No, right? The answer is no. There is no 60%. From 83%, there's a direct jump to about less than one. I mean, less than it's about less than 7%, right? Why do you think it happened? From from about 84% to you have a value of 7%. Can you answer why it happened? What do you mean by liquid formation? It's in vapor phase. Uh, can you have a better explanation? Do one thing. Think over it. Okay. Spend some time on it. Think over it. Don't answer it now. Think over it over this week and answer it in the coming week. Okay. Why there is a sudden jump from 84% to 7%? Think over it and come back next week. Okay. So actually, this is what I had planned for today lecture. If you have any doubts, we can discuss it, or else we can come back in the next week and then proceed further in the simulation of a separation plant. Have any other questions? Yeah, the question. Okay, I'll show you this question. Question or the Aspen? Aspen. Do a simulation first of all. Once after simulating, you'll have the same data. Okay, from that data, try to do an interpretation of this. Why there is a sudden jump, and come back next week. Any other question do you have? Yeah, yeah, I'll upload this video in 5-10 minutes just after the class. Every week I'm uploading immediately after the class. Anything else? So in that case, can we stop this lecture for now and come back the coming week? Fine, we'll do that sensitivity analysis or the whatever optimization. In fact, we'll do a couple of optimization problems. So you'll have a good exercise of model analysis too. My mail ID, it's ch18d700 at smail.iitm.ac.in. I'll just put it in chat box. Any other questions do you have? Okay, so in that case, can we come back next week? Do have Aspen in the next session. Okay, we'll have good exercises. Okay, then have a good week. See you.